Hi, today we start our Chapter 2 notes. In our first lesson you can see that we're looking at complex numbers, but to give you a larger overview, Chapter 2 is about polynomial and rational functions with an emphasis, a dual emphasis, on doing algebra to find their solutions, but also being able to graph them both with technology and by hand. So very important process in algebra, polynomials and rational functions. And we're going to begin today by talking about the complex number system. You will remember that the imaginary unit I is defined as the square root of -1. I is equal to the square root of -1. That whole being able to talk about that square root of -1 is totally unusual, right? Because we've always learned that you can't have negatives under the radical. However, by creating the imaginary number I, it allows us to do computations that we would not have been able to do otherwise. So just having I in our vocabulary leads to a new set of numbers called the imaginary numbers. Which are numbers in the form a plus bi, where a and b are real number parts, so they are real coefficients. A is called the real number part of this thing. The real part is how our textbook puts it, and b is the imaginary part. Now together with the real numbers that we know and the imaginary numbers that we're going to talk about today, those two sets make up the set of complex numbers. We're going to be studying those complex numbers more thoroughly as we go through this course. To add or subtract complex numbers, you do what you think. That is, you combine like terms. And I would love to have you think about that. Like terms. You combine like terms. So as I'm looking at this addition, I think to myself, okay, there's a 5 with no I, and to be like it, you also have to have no I, so that 3 goes with. 5 plus 3 is 8. This term and this both have an I, so I should be able to combine them. -2i plus 3i is 1i, or just plain old I. So there you go. When you add or subtract, you're combining like terms. I want to give you a chance to do this one. This would be a great place to pause the video, see if we come up with the same result. Okay? Alright, here's our real number parts. So we have 2 plus 12. Oh, it's 2 minus 12. That's -10. And here are our two imaginary parts. We have 6i minus -i, and subtracting the negative means positive, so we have 7i there. -10 plus 7i. Is that what y'all got? Hope so. Alright, multiplying complex numbers. You know, the properties for real numbers extend to the complex numbers. You can do the same things with complex numbers that you can with real numbers. There is one little thing, though, that's very helpful to remember. That is that I squared is equal to, so think about this. If it's just I, that's the square root of -1. I squared would be multiply that by itself. And when we multiply radical times radical, we get rid of the square root signs. That is, the square root of -1 times the square root of -1 is -1. I squared can be replaced in any expression with the value -1. So that's going to help us out here. Let's try this one. We have a distribution. So that 7i has to be distributed to both places. 7i times 2 would be 14i. And then we have 7i times 9i, and that was negative. So minus, let's see, 63i squared. We're not quite done yet, because that I squared has the same value as -1. I'm going to just put that in parentheses up there. That means -1. And that means that that expression simplifies to 14i minus 63 times negative 1. Well, minus a minus is plus. You guys, that's positive 63 right there, and I'm going to write that 63 up front. So we're talking 63 plus 14i. Okay? When we did that distribution, we came up with another imaginary number. We replaced I squared with negative 1 and did the work that way. Negative 1 times negative 63, positive 63. All right, here we have quantity times quantity, and nothing's changed here. We are either going to use the box method, or we're going to use FOIL to help us do this multiplication, whichever is your choice. And I've been using the box method a lot. I think I'm going to use my favorite, the FOIL method here. First times first would give me negative 14. Outsides, that's a 7 and a negative 5i, so negative 35i. Insides, negative 3i times negative 2 is 6i. And finally, the two last terms, negative 3i minus 5i, we're multiplying. Negative 3i times negative 5i, that's 15i squared. And I'm going to remember that that I squared is like negative 1. I'll write that down here. And then I'm going to start combining things together. Negative 1 times 15 is negative 15. Negative 15 and negative 14 is negative 29. And I'll just write under here, that was a minus 15 after we changed that I squared to negative 1. Then we combine our imaginary parts, negative 35i plus 6i. That's going to give us negative 29i. And there's our final answer. Negative 29 minus 29i is the result of that multiplication. So we multiply just like we do with real numbers. Our next operation today, dividing complex numbers. Since a complex number by definition has or can have these two parts, you can divide complex numbers by multiplying top and bottom. Multiply top and bottom, numerator, denominator, by the conjugate of that imaginary number in the bottom. So, oops, conjugate. Just a quick reminder, the conjugate of a plus bi would be a minus bi. It uses the same two elements but with the opposite sign. And when complex conjugates like a plus bi and a minus bi are multiplied, something really cool happens. And I want us to see that. So I'm going to ask you to come out here for a minute, and in my famous margin math out here, I want to multiply a plus bi times a minus bi. A plus bi, a minus bi. A times a squared. Here we have a positive or a plus abi. Here we're going to have a negative abi, and right there is where the magic happens, folks. Here we have bi positive times bi negative. That's going to give us negative b squared I squared. And I just want you to take a look at this for just a minute, realizing that I squared acts like negative 1. I'm going to write that right there. When we start collecting like terms in this thing, we're going to get a squared. Here we had a plus abi, here we have a minus abi. They add up to 0, or they go away. And here we have negative b squared times negative 1. Folks, that's the same thing as positive b squared. So whenever we multiply complex conjugates, we're going to end up with the first term squared plus the square of the b coefficient. Okay? A squared plus b squared. That's always going to happen. And that is pretty cool. So, as we multiply 3 minus 2i times 3 plus 2i, we could do the box method or FOIL, which I'm going to show. Let's see. It would be 3 times 3. So first, 3 times 3 is 9. Outsides, 3 times 2i, 6i. insides minus 6i, and last, negative 2i times positive 2i, that's minus 4i squared, which again, that's negative 1, so would come out to be plus 6i and minus 6i are going away. We have a 9 plus a 4, which is exactly what our pattern said we should have, square of this plus the square of this, or in this case we can further simplify to 13. So there's a good multiplication of complex conjugates, and let's apply it. If we're going to divide, which is why we're doing this, what we got to think about is we're doing 5 minus 3i divided by 1 minus I. The rule says you multiply top and bottom by the conjugate of the bottom, so 1 plus I down here, 1 plus I up here. And as we multiply here, we're going to end up with 5 times 1, which is 5. We're going to have 5 times I. Insides, negative 3 times 1, or negative 3i times 1, so minus 3i. And here, negative 3i times I, that's negative 3i squared. And we'll simplify that in a moment. On the bottom, we should be able, folks, to use the pattern here. We're going to get a squared plus b squared, and remember there's no coefficient with that I, so it's 1. That means we should, if the pattern works the way it's supposed to, get 1 squared plus 1 squared, which is 2. If you don't trust me on that one, you should try and do that FOIL or that box method by yourself and make sure that you get that same answer. That is correct. 1 squared plus 1 squared is what's coming out of there. Now it's time for us to deal with we have the numerator, or the denominator, taken care of. It's time for us to deal with the numerator. I see we have some like terms, and I see here that I squared. So I know that that's the same as negative 1. Negative 3 times negative 1 is 3. 3 plus 5 is 8. So we're talking 8. And then we have plus 5i minus 3i. That's 2i. In the denominator, we had 2. 2 divides into both of those terms, so we can do that division, and we're going to end up here with 4 plus I as our final answer. 4 plus I. We did the division by multiplying by the conjugate of the denominator. Try this one. This again would be a great place for you to stop the video and make sure that we come up with the same thing. Going to multiply both top and bottom by 4 plus I, which is the conjugate of the bottom. We're going to think bottom first, maybe, because that's the easier math. Pattern says if A is 4 and B is 1, then we should be getting 4 squared plus 1 squared. That's 17. On top, 5 times 4 is 20. That was the first. The outsides, 5 times I, 5i. You may have used the box method, which is certainly okay. 4 times 4i is 16i, and 4i times I is 4i squared. However, we know that I squared is negative 1, so we're going to simplify a little bit here. That's going to make that minus 4. 20 minus 4 is 16. We have 5 plus 16i, that's 21i. And all of that over 17. And we've divided our complex numbers. Very good. All right, let's see what else is in this flip chart. Oh, here's one of the big reasons why we need those imaginary numbers, because there were quadratics that we could not solve before, but since we have those complex imaginary numbers, now we can. To solve a quadratic that's in general form, like this one, ax squared plus bx plus y, or plus c, sorry, equals 0. Okay, if we're going to solve a quadratic that's set up this way, you use the quadratic formula, which says that x will equal the opposite of b over twice a plus or minus the square root of b squared minus 4ac also over 2a. There's our quadratic formula. All right, this says we should solve these and put our answers in simplest radical form. So that means if we end up with square roots in our solution, we're going to leave them that way. We're not going to go to the calculator. In this one, a is 1, b is -6, c is 10. So as I'm going to solve this guy, I got to be thinking x will equal the opposite of b. So it was -6. Its opposite is 6. 2 times 1 is 2, plus or minus the square root of -6 squared, which is 36, minus 4 times 1 times 10, and all of that will also go over 2. Simplifying, x will equal 3 out front, plus or minus, under the radical, 36 minus 40, and that is 36 minus 40, -4. All over 2 that was. All right, I can take the square root of -4 because the square root of 4 is 2, and the square root of -1, folks, is I. So that means that our x's are 3 plus or minus 2i over 2. And we can certainly simplify that last to say that our x's will be in the form 3 plus or minus, and the 2's cancel. So 3 plus or minus I are our two answers for that quadratic. Cool, huh? I'm going to ask you to do one more problem like that. I will just caution you though, this one is not set up in the right form yet. So before you begin operating on this guy, you need to subtract 8x and add 7, and I'm going to do that right out here. So we're talking 3x squared minus 8x plus 7. Just got to move everything over on one side, equals 0. Now we're good to go. Quadratic formula says that x will be equal to the opposite of b. So it was -8. Now it is 8 over twice a. 2 times 3 is 6. Plus or minus the square root of, let's see, b squared. -8 squared is 64. Minus 4 times 3 times 7, a and c. All of that also over twice a 6. Let's see. That's going to give us, well, that reduces. I'm going to make it 4/3 right now. Plus or minus, and then I got to think about what's under the radical here. 4 times 3, well, it might be easier to go this way. 3 times 7 is 21, and 21 times 4 is 84. So we're talking 64 minus 84, that's -20, all over 6. -20, not going to worry me because I know that that's 4 times 5 times -1, right? So you could be thinking out here, I usually would not write this, but that's -1 times 4 times 5. I can take the square root of 4. I can take the square root of -1, and that 5 is left under the radical. So our x's are going to be 4/3 plus or minus 2i times the square root of 5 over 6. The only thing that could make this better is doing that little reduction right there. So in simplest radical form, our answers are 4/3 plus I times the root of 5 over 3. 2 goes into itself once, 2 goes into 6 3 times. So here are our final answers, 2 of them because we have a quadratic. So everything works out fine in number land today. I hope that you enjoyed this video, and I hope that you will get quickly to the U-Try for this section, and I'll see you in our next class period.